This is Professor Jimenez, and now we will see the memory map banks 0 through 7 for the PIC16f1619. On the left side here you can see that bank 0 in these locations 0, 0, C, D, and E. It has port A, port B, and port C respectively. So we know these are the most important locations for these ports, and this is where you can read or write data in digital or analog format. And also you have in this in bank 1 the memory map, you have trace A, trace B, and trace C. These registers control control and configure every one of these ports. So you want to make port A equal to input, equal to an input, the whole port. Trace A must be equal to all ones. If port A, for example, is made of 5 bits or 6 bits, you need 6 bits equal to 1. And then same for trace B. This one controls if port B is an input or an output. If you want to make, for example, port C equal to an output, all port C with its 8 bits from RC0 through RC7, you have to clear 3C. So 3C must be equal to all zeros. The whole byte should be zeros. And so you can clear this clear file 3C, and this port will be an output. Now, there are other registers called lat A, lat B, lat C. This is the abbreviation for latch A, latch B, latch C. So you want to read the status of the latch in these bits. You have to clear them, or you have to read them from there. It's not the same reading data from a latch bit, latch register or latch bit, than reading data from a port. Okay, we will see those details later. And if one of these ports you want to make it analog, for example, to read a voltage, uncell A for port A, analog selection for port B, analog selection for port C. In those registers, you configure which pins you want them to read an analog voltage. Okay, if it is a 1, if they are 1s, you want to read a voltage. If they are 0s, you want to read a digital input, 0 or 1. By default, they are all 1s. So you can find that in the memory in the description of every register. So a common error is when you start a code, you have to clear this, all of them, and then configure them. If you don't configure those, your ports right here will be, by default, will be analog. Okay, so you can't read any digital input unless you clear these ports. So the first part in any code that you're writing is that you have to clear and you have to configure and clear the registers according to your applications. Every port okay, look at this. This is on bank 3. On bank 4, you have other registers called WPUA, weak pull up port A, weak pull up port B, weak pull up port C. So these are weak resistors. We call them weak because they are they have an average value of 80 kilo ohms. So these resistors by default are disconnected. These resistors allow you to pull up a port without having to use external resistors. That way the port will not be floating. Okay, and in other old micros you will have to put the external resistors. Of course, sometimes you might decide to put them, but if you want to make use of them, you will save hardware. There are other registers like the outcome odd counts configurations and slew rate configurations, which allow you to control what type of signal you're going to be reading, the slew rate, and also you can use this type of registers to control other features in the ports. Okay, other important parts of those ports are the timer, the interrupt registers are these timers, timer 0, 1L, timer 1H, which is very common for us to use in many applications, is in this location, 16H and 17H. Okay, timer 2, timer 1 gate configuration. If you want to gate to control externally the input frequency, you can do it with this register. Timer 2 configuration, these are older registers, and you can also you also have the option reg, the option register, okay, where you can configure other features of the port. OSTUN, OSCON is to configure the speed of the clock. If you're going to be working at 1 megahertz or even lower, 32 kilohertz, 1 megahertz, 8 megahertz, 16, 20, or using an internal PLL to increase the clock to a higher frequencies. And address low byte, address H. These are used for the analog to digital converter low byte result. This is a high byte result from the A to D converter. And this is how you configure the analog to digital configuration, register 0, A to D configuration 1, A to D con 2. Okay. There's also a DAC, a digital to analog converter, which you can configure with these two registers. Okay. So these are the most important ones, but we have to see them in detail. At this moment, what is important to know is the locations, so where they are. Okay. And you can use them in the code by a name or nickname that you give them, but you have to establish their location. That way you don't need to always remember the exact location. Okay, and look at this. This is the common RAM that you have available. These are the range of those common RAM. Right here you have 96 bytes. Right here 80, 80, 80. Okay, for GPR, general purpose registers. If we see other, as we can see here, other banks, like bank 8 through bank 15 in this page, you can see other registers that allow you to configure it for timer 4, okay, timer 5, timer 3, the PID proportional integral derivative system. You have to set it up right here. You have to configure it. This is used in engineering for control systems, and so the clock generator, the waveform generator with a band gap. So this one is used for inverters to convert DC to AC. The watchdog timers. Let me move this a little bit. The watchdog timers are here. Okay, another registers called scan. These are CRC for configurable logic, and there are other banks too, like bank 16. You see, we have all these registers, and so on until you reach bank 381, which is the last one, bank 381. And so this is how all the banks are configured. And there are other banks like map banks, bank 27, bank 28, their locations. If you're going to need them, you need to know where they are located. In our next video, we will see how to configure these ports. So we have to see more about the hardware. It is not convenient to just watching all these or learning about all this in one single lesson. No, like a summary of this class, today's class, is that we are learning about port A, port B, port C, the trice registers, the latch registers, and cell, WP, UAs, B and C, and the other ones right here, address L, DACs, timers, which will be the ones most commonly used in this class. Also, we will see the CM1, the configuration 0, CM1 con 1, and okay, brownout reset, in the voltage regulator, the brownout reset in case you want the micro to reset if the voltage is lower than 3 volts for battery applications. And this zero control detection, this one is used for alternating current to control the power in many types of motors or resistive loads, AC loads. So this is for synchronization with AC alternating current loads. Okay, well, this is all for this lesson, and thank you very much.